Good morning, YouTube. What's going on, people? It's snowing out. It's a nice day, though, otherwise. And we're going to solve some math problems. In fact, hard math problems. What's up? I'm Greg from GregsTutoringNYC. And this is part of a series here. We're on part 3 of grade 3. And just before we jump in, please like and subscribe. This is a lot of work for me to do, so give me some incentive backwards. There's more of these coming. I'm going to do them for all grade 4, grade 5, grade 6, grade 7, grade 8. And if I can get through all that, we're going to start doing other material as well. So I did a part 1 of this, about 30 videos, in addition to all the other videos that I do. And there was multiple choice math problems. These are show your work math problems. They're being sourced from the New York State exam, and these are questions that most students were not able to answer. Not talking about 10 or 20 students, we're talking about a few 100,000 students. All right, so these are definitely the hardest math problems for one reason or another. The past videos can be found through that link that's on the screen right now, GregsTutoringNYC.com/hottest-math. Okay, and if you guys are catching this on the replay, you can pause the video, try to solve it yourself, and then see what my solution is. What I'm trying to do is I'm less trying to do this as standardized test questions, but in that these are concepts and topics that seem to be the ones students are struggling with for one reason or another. Maybe you go to a bad middle school, maybe whatever the reason is. These are the ones that are creating problems for the most children. So these are the ones I'm focusing on. There are other definitions of hardest math. This is the definition I'm using, at least to do these. And there's enough problems and enough confusion. And what I'm going to also, so I'm going to focus on the concept and topic aspect of it. So when possible, I'm going to try to point out what are they actually testing you on. Okay. Sometimes the concept is really simple, and sometimes it goes deep, and sometimes it crosses things. So I could say it's talking about equal parts, and it's also dealing with triangles or something. So that's a geometry and an arithmetic question at the same time, all right? And that's part of the issue where, like if you get a word problem, that could be why it's hard to solve sometimes, all right? Okay, so with that in mind, please like and subscribe. And let me just jump in here. Let me try to get my computer showing what it needs to show. Let's get rid of that. Okay, and I'll also explain the basis of why some students may not have gotten a full score on these. Now, a lot of these are traditionally worth 2 points. Some of the ones a few questions down, there's about 5 to 10 questions I'll do here that'll take up about an hour. The first half are normally worth about 2 points, and the second half of them are going to be worth about 3 points each. And sometimes, if you notice on here it says explain your answer, you just can't repeat the math. If the question is 1 plus 1 equals what, well, the answer is 2. And then they say explain your answer. You just can't say 1 plus 1 equals 2. That's not an explanation. That's just repeating the fact. Okay? You have to basically say you're talking about the concepts again. If I have one thing and I add another thing to it, now I have 2 things, right? That's the rationale behind it mathematically, as well as logically, as well as the English. So you're not just always just repeating 1 plus 1 equals 2, and therefore 1 plus 1 equals 2. That's not a justification, right? So that's where they're going with some of these. All right, give me 1 second. To bring up that there. Okay, there we go. So let me see if my tablet's going. I'll scribble there. There we go. So it says, there's no illustration. Write a fraction that is less than a third, using 1 as the numerator. So it's telling us, first of all, you should know that it's numerator over denominator. Okay? If you get confused on which is which, just remember one or the other of them. I have something called the rule of 2, which is normally a rule of x. And it goes as follows. Is this two things to memorize? Just memorize one of them. If you memorize one of them, you know what that thing is. That leaves, well, what about the other one? The other one is not the other thing. So if you memorize that a numerator is on the top, that's all you have to do. So all you have to do is set up a numerator over here, and then you're left with the question, what's the denominator? Since this is empty, it's got to be that. Okay? So this way you don't have to memorize two things and keep getting them confused. It's numerator over denominator. So getting back to the question, it says using 1 as the numerator. So it's telling us we have to have 1 over something. Let's call it x. Okay? And in particular, it's telling us that it has to be less than a third. So basically, we're going to have something over here is less than a third, and then something else is going to be greater than a third. So since they said the numerator has to be the number 1, we're looking at 1 over something, let's call it x, is less than 1 over something else. And we're going to talk about this conceptually. 1 over y is less than something else. Whoops. And 1 over z. We have to compare 3 things here. And they're telling us specifically that this one here is a third. Okay? So basically what we need to do is figure out what the y, the x, and the z should be. Okay? So if we go back, if we're looking at this right here, let's go back to the English, write a fraction that is less than a third, using 1 as the numerator. Okay, so that's what I have. I have 3 fractions down here, where this one's going to be less, the x is going to be less, and the z is going to be whatever. So one way to solve this is to just plug in numbers. So if I put 1/4 here, is that less than a third? Or is 1/4 greater than a third? Okay? On the same note, if I use a smaller number, like 1/2, is that less than a third? Or is that greater than a third? Okay? So we have to get this scenario where we're actually doing this comparison here. So you should be able to observe that a quarter is less than a third, and a half is greater than a third. You should know this already. But if we do it visually, right, and this gets back to the concept of a whole, and then equal parts. If I take something, this rectangle here as a whole, right, and I split it into thirds, and I'm going to do this by eye, it doesn't have to be exact. So I have 3 parts, 1, 2, 3, right? Okay, if I put a second exactly equal rectangle underneath it, okay, and I split it in half, and now I have 1, 2 parts, okay, and I take another rectangle, which is supposed to be exactly the same one again, and I split that into quarters, 1, 2, 3, 4, okay? So if I look at rectangle A, rectangle B, and rectangle C, is it not true that these parts here with the quarter are smaller than the parts in the half, because there's only 2 parts here, and also smaller than this 1/3 parts, right? Is it not true that the 4 parts in C are smaller than B and also smaller than A, right? Which actually is our last statement here. Well, actually I have it backwards. So what we have is a 1/4 is less than a 1/3 is less than a 1/2. Okay, that's the visualization of those 3 fractions I just wrote there. So you can visually see that the 2 parts in B are greater than the 3 parts in A. And the 4 parts in C are smaller than the 2 parts in B, and the 4 parts in C are smaller than the 3 parts in A. So from that, we can determine what they're asking us to do. It says write a fraction that is less than a third. So one answer is a quarter. Okay? And then it says explain why. Well, when a numerator is the same, we can either pick a denominator, right? We're comparing it to a third. So if you go back to this 1 over x and 1 over z notion, right? Do we make it larger or smaller? Well, our tests, our experiments that we did here tell us that if the denominator is smaller than the third, right, which is the half, then it's larger. Okay, and if the denominator is smaller than the 3, then it's less than. Okay, so that's the answer. What I just said is the answer. So I could have also chosen a fifth. A fifth is smaller than the third. Okay, 1 over 999 is smaller. And we can see that as the example, that if we took the rectangle again and just split the daylights out of it into 999 parts, right? Isn't it true that every single fraction here, 1 over 999, isn't it true that that's less than a third? We can see that visually. That's so many little tiny parts at that point, right? So first of all, you should know this rule. You should know that 1 over something. And when you compare it, and by the way, it'll work the same way if it was a 2, as long as the numerator's the same. So 2/4, right, is less than 2/3, is less than 2 over 2. Could have been something we did there, right? And we know 2/4 is the same as a half, and this is actually 1, right? So isn't 2/3 greater than a half? Again, we can do the same kind of visualization. So we're going to write 3 rectangles. Okay, this is the one that's 2 over 2. It's the whole. Okay, the next one is 2 out of 4, so that's this here. So that would be a half. And the next one is split into thirds. So it's 2/3, right? And this was the whole one here. So isn't it true that this middle one is between the shade, if we shaded these areas? Isn't it true that the middle shaded area is between the top one and the bottom one? All right, so that's where we're going for this kind of a problem. So this was about splitting a whole up into equal parts, more parts in particular. Okay, it's also about comparing a fraction, 1 over x, versus 1 over y, that kind of a thing. It's also slightly about knowing your division, which is also about knowing your multiplication. And just how to compare the denominators. So it's not intuitive. So the answer was, as the denominator gets larger, the fraction gets smaller, right? That seems to go backwards to what intuition would tell you, right? Again, as the denominator gets larger, the fraction gets smaller, right? Let me just scroll this slightly. So as the denominator gets larger, if I have 5 over here, that has to be less than a quarter. It's also less than a half. It's less than a third, right? Right? And the same thing if I keep getting larger, a sixth, a seventh, an eighth. These are all smaller than all the fractions I listed over here because the denominator is larger. Okay, there is a second way to double check some of these. It's called the cross product. Some of you may or may not have learned this, so I will throw it out there for now, which is you write your 2 fractions. Okay, this was the target fraction. We're going to put the arrow here. What we're going to do is we're going to multiply the numerator of the one fraction against the denominator of the other. So we have 3 times 1. This goes up. So we're going to write that answer, that product, above it. Okay, we're going to write a 3 there. Okay, and then we're going to do the same thing with the 4 and the 1 here. Okay, and we're going to write that product above that. Whichever number, the 4 or the 3 is larger, is the larger fraction. So therefore, since 4 is greater than 3, we can do that. Okay, and this is true even when the numerator is not 1. All right? So we can use my example where I did before of 2/4 versus 2/3. Again, we do that. 3 times 2 is 6. We write it where the line is pointing up. 4 times 2 is 8. So 2/3 is greater than 2/4. And we can basically pick anything. We can do 5 over 6 compared to 10 over, let's say, 4. 5 times 4 is 20. And 6 times 10 is 60. Okay, and we can write them in the reverse order. We could have wrote 10 over 4 compared to 5 over 6. So 10 times 6 is 60, and 5 times 4 is 20. So in this case, we would be doing this. 5/6 is greater than 10/4. And over here, we're doing it the opposite. 10/4 is greater than 5/6. These are mathematically equal anyway, the two groups of fractions, the way we compare them. Because the 10/4 is always the largest one in both scenarios. All right? All right, so I've totally really beaten this one up. Okay? In fact, we're almost 17 minutes just on this one question. I like to be meticulous and thorough. Again, once you see the answer or you're clear on it, you can obviously skip to the next question, especially as we're doing this on the replay. So again, it was about comparing fractions with like numerators. That was really what the question was about. Okay? Okay. So again, this is a word question. Patty has 40 marbles. So we have a bag. And we have a whole bunch of marbles. 40 of them. Okay. Each marble has 3 grams. So one marble, if you notice, I'm taking it a sentence at a time. Patty put there, each marble has 3 grams. So one marble is 3 grams. Okay. What is the total mass of the bag of marbles? Okay. So first of all, you have to cut through the chase here. It's assuming the bag of marbles don't count, right? Because let's say I say each marble is worth 1 gram, then you know that's 40, right? If we're going to take a sidebar here. So if one marble was 1 gram, then that means 40 marbles would equal 40 grams. So that means there's 40 grams inside of here. And then you're left with the question, what about the weight of the bag? We don't know the weight of the bag. They're not going to tell us that. Okay, so this question is poorly worded slightly. It should have said, what is the mass of the marbles in the bag of marbles, or something a little cleaner. All right? All right. And by the way, just to give us a hint, they're looking for grams as the answer, just in case some kids think it's about marbles. This is not about doing 40 plus 3 and getting 43. That's adding marbles and grams. That's not the way to do this. Okay? So what we have to do is finish our comparison here. That if 1 gram is 3 marbles, then 40 marbles is how many grams? Okay? So we can solve this just the way we just solved the other problem. We can do the cross product. Okay? So we get 1 marble times x here. So we get x. 1 times x is x. And then if we do this one, we get 3 times 40. Okay, and that's equal to 120. So that turns out to be our answer, 120. All right? Whoops. This is trying to outsmart what I'm doing here. Be nice if it made it a circle. I think it has a way to do that, but I'm not worried about that right now. So that's the way to do this. That's one approach to this. So this is talking now about multiples. Okay, it's talking about equal parts because each marble is 30 grams. Equal parts, multiples of it. Okay. You could have also done this logically, right? So again, if we get back to what I was saying earlier, if one marble is 1 gram, then if each marble is 3, right? We can just multiply it by 40, right? If there was 1 marble is 1 gram, sorry, I'm saying that wrong. If 1 marble was 3 grams, how much is 1 marble? 3 grams. So how many is 2 marbles, right? So we have 1 marble gives us 3 grams, right? 2 marbles would give us 6 grams. 3 marbles, right? We're just adding by 3s, would give us 9 grams. Okay, so we can see it's the number of marbles times 3. And that's all we can do. So you can count up. You can do 3, 6, 9, 12, and go all the way up 40 times. You'd have to do that 40 times. And eventually you get up to 127, and then the next one would be 117, and then finally 120. Okay, that's tedious. You don't really want to count that out 40 times. All right, but it's technically possible. If it said there was like 3 marbles, then you could just do this as simple as that. And if you notice what I did on the previous question, I did this little experimentation with the fractions over here. I did the experimentation visually, okay? And I'm doing that same kind of thing on this question. This little sidebar exploration I did just to kind of mathematically make sense of what's going on is part of what you need to do, okay? It's part of what you need to do. This way, it's good to memorize stuff, but memorization is roteness, and that's not mathematical proficiency. Even though your knowledge and you should be able to be fluid in your math, like knowing the multiplication table is really important, but it's not a requirement to understand the concepts. But at the end of the day, you need to know it all. To be mathematically proficient means to be doing each part well. You don't want to be doing at this point the multiplication table on your fingers. And if anybody needs lessons in learning the multiplication table or whatever, please email me at the bottom of the screen there, and I can get you guys to be proficient on the multiplication table. And by the way, grade 3 is normally the line in the sand where you're supposed to be learning the multiplication table. And it means all the other math you do for all the other years, once you do that, and I'm not trying to trivialize it, it's annoying and hard to do. Once you know it, though, that's it. You don't need to keep memorizing it. It becomes so easy to do a lot of stuff, especially as each year goes on. Even when you get into algebra, you still have to kick back down to arithmetic, and you still need to know your multiplication tables and things like squaring numbers and doing 2-digit multiplications and 3-digit multiplications and decimal divisions and all this kind of stuff. It all roots on having to know how to multiply and divide just single-digit numbers and so on. So it gets to be important. There are strategies to break numbers down like 25 into 20 and 5, but if you don't know the root stuff, even that gets elusive. In a lot of cases, doing that split down takes longer and is more error-prone than just knowing some of these things straight up in the first place. All right, so I took a couple sidebars. So that's all this problem is about. We can do this version here. Let me just change my color of the pen again. So first of all, I did this thing where we set up the cross product as the fraction. That was one way to do this. Another way was this here, where we just set up a table and just started writing them out to try to see if we can see what the pattern was going on here. Some patterns are more involved and complicated than others. This was a pretty trivial problem in terms of the pattern. Okay. Okay, just to go into what some of these weren't, I said over here that it wasn't 40 plus 3. it was also not 40 divided by 3. Okay? It's not taking the total number of marbles and dividing it by the mass of a marble. So it's not 40 over 3 equals something. Okay? It's not that either. That's not what this problem is. Some kids also, they can grok the part about this here. And by the way, you could have done this straight up. I wrote this, I'm going to label this part D right here. I wrote this as a consequence of doing the cross product, but you could logically see that it's D straight up. You can say, oh, there's 40 marbles. Each marble's 3 grams, so it's 40 times 3. You could do that straight up if you had wanted to. What some kids do, though, is then they do 40 plus 40 times 3. Okay, and they end up getting, what, 160? This 40 here doesn't belong. There's no reason to add another 40. 40 isn't the weight of a marble, and it's not. So what you're doing is you're adding a marble weight plus just the number of marbles. That doesn't help you. So you're combining like terms here in algebraic sense. That's what I was talking about. So it's not this either. All right. So this was dealing with multiples again. It's also dealing with knowing how to deal with numerators and denominators. This thing I did with A, when I originally set it up, I said it was the cross product. But we're talking about a ratio. 1 marble is to 3 grams. That's a ratio. And when I do the 40 marbles to X grams, I've now set up a proportion. The proportion is trying to compare the two ratios. And when I finally get the answer 40 over 120, that's also a ratio. Okay? And we want to see if it can kick down to 1 over 3. All right? That's all we're doing there. All right? And there is a repeated addition version of this as well, which is similar to this right here. We could have done 40 plus 40 plus 40. Okay, and got 120. Okay. This means that if there were 40 marbles at 1 gram, then it would be 40 grams, right? So that's this first part here. If there were 40 marbles at 2 grams, then it would be adding another gram to each of the 40, and then finally doing that. So we're kind of doing it in layers and trying to finally get there. All right, so that's another way to do it with repeated addition. So these two ones here are kind of analogous because repeated addition is multiplication. All right, so we need to know about our equal parts and we need to know about our multiples. So the answer would have been 120 there. Okay, so we have a visual. I see 3 triangles. I also see a greater shape, which is a trapezoid. I don't know what they're going to do here. I don't know what they're going to ask us. This one is super hard for me to grok what they're really looking for here. I believe those might be equilateral triangles, 1, 2, and 3 there, but I don't know what they're doing because they could have done something like this. Remember that unless it tells you, things are not drawn to scale. So the 3 triangles could actually be that 1, 2, and 3. So this just happens. This just happens if I call this length A from here to here, and this length B. It just happens to look like A is equal to B. Okay, but I don't know for certain. So it's going to have to tell me things like that. Otherwise, I can only make inferences, and those inferences could be mathematically erroneous and incorrect. All right, my voice is giving out at me, so I don't know if I'm going to be able to get through this completely. Plus, I have other sessions after this. So, all right, let's go back to the words. Ved drew the shape below. Cool. By combining exactly 3 triangles. So 1, 2, 3. That's what we saw here. Of the same size and shape. So it's telling us that triangle 1 is equal to triangle 2 is equal to triangle 3. And just give me 1 second. I want to make sure you guys are seeing that on the screen. Oh, no, you're not. Sorry about that. Let me just drag that down slightly. Okay, there we go. So these are exactly equal. That's called congruency. This is a terminology word that you normally learn in later grades, but I might as well throw it out there. By definition, congruent is the same size. I'm going to put SS and same shape. SSSS. If two shapes have the same size and the same shape, then they're equal. They're the same shape. So some kids get confused and say, well, you know, 1 is definitely equal to 3, but 2 is upside down, so it's not 2. Yeah, but if we can take 2 and overlay it on top of 1 and 3 and put them all overlaid on top of each other, and it's the same shape, they're congruent, all right? Same, we can take, let's say I can take this same shape here, and if I was to flip it and tell you it's exactly the same shape, whoops. It doesn't matter that they oriented different. They're still the same size and shape. So they're still congruent, okay? They're transformed. If one's upside down, it's been transformed, but that's a different story. So let's reread. We do the shape below by combining exactly 3 triangles of the same size and shape. What fraction of the area of the whole shape is each triangle? So it's telling us that they're exactly equal. So the trapezoid is the whole. That's the whole. We had other examples where we had a number line, if you remember those from part 1 or whatever. We had 0 and 1, and I said that's the notion of a whole. Well, this whole trapezoid, the whole inside of here, that's a whole trapezoid. Okay? So if triangle 2, and triangle 2 are equal, then it seems to me that the fraction here is a third. Because there's 3 equal parts. So now we have a different visual way to look at fractions and equal parts. We spent a lot of time in the past 2 sessions doing problems involving number lines. So this is a whole divided into equal parts. That's it. And we get a fraction. So this fraction number 1 is a third of the whole trapezoid. Fraction number 2 is a third of, triangle 2 is a third of the whole thing, and triangle number 3 is also a third. And if we can see that 1/3 plus 1/3 plus 1/3 is going to be equal to 3/3, and that's all the parts. And we know that a number over itself is equal to 1, except in cases when the denominator is 0. So that's true for all numbers except for 0. Any number on top of itself is 1. So just as a sidebar, I'm telling you that anything over 0 is undefined. So this will not work even if 0 over 0. That doesn't work for that either, okay? So that's our concept, is a whole divided into equal parts. We can do it many ways. We can do the third plus the third plus the third equals 3/3 equals 1. Or we can just observe. If it's a whole and they're dividing it into 3 triangles that are the same size and shape, then 1 and 2 and 3 must equally be equal parts. There's nothing else left, right? If we take triangle 1, 2, and 3 and start removing those parts of the trapezoid, once we remove the 3, we remove the 2, there's no trapezoid left. So they're equal parts. Okay, there's nothing else there. Okay. Okay, and by the way, this 1/3 here, let me change the color of the thing here. Let's bring it back to red. Okay, the fact that this is 1/3 has nothing to do with the sides of a triangle A, B, and C. That 3 has nothing to do with that, there's things. We could have said there was a rectangle, and I'm drawing this sloppy or whatever, but and that this A, B, C, and D were equal parts. But if you notice, there's a pattern that emerges that each rectangle that I did has 4 sides, right? And if we did it 4 equal parts, then each A, B, C, D would have been a quarter. Okay? But is there other ways to orient that? Because, for instance, I could have added on here 2 more and got an E and F. So in this case, each would have been 1/6. So you just can't go by the number of sides of the inner shape. Okay? The inner shape being A, B, C, D, E, F, and the outer shape being the whole giant, the super rectangle, if you will. All right? So you just can't do that. So we're not just looking at the number of sides A, B, C, and saying there's 3, so the answer is 1/3, right? So you can't do that. And there's another slight confusion to this, because you could argue that, let me scroll this slightly, that in the trapezoid, if we have the 3 triangles A, B, and C, okay, can't you argue that triangle A is its whole self, and triangle B is its whole self, and triangle C is its whole self? Yes, but they're part of the trapezoid first. So you just can't say the triangle as a whole, and therefore the answer is 1. Okay? So that's, some kids get confused with that, because it says what fraction of the area of the whole shape is each triangle. And you can't misinterpret that and say the whole shape of the triangle is the triangle. That's not what the question is. The whole shape they're talking about here, right here, that's the trapezoid. They're not talking about the triangle there. So be careful as you read these questions. They can be, they involve attention to detail. Make sure you're keeping track of what's going on with what. Because some kids end up saying 3/3. Again, for the same reason, that it's the triangle. Right? Some kids say it's 1/3 because there's 3 sides of the triangle. Some kids are saying the whole shape is the triangle, and therefore it's 3/3, and it must be 1. Right? But 1 is not working, because it's the parts of the triangle out of the trapezoid, not the parts of the triangle out of the triangle. Okay? So be clear with these. These are where kids go down, it's called going down a rabbit hole, and you start getting confused about what you're even being asked to do. And even though this isn't quite a word problem, it has words, and you still need to match it back to the math and the visual and the whole thing. That's the dilemma here, and trying to resolve a lot of these and get to the bottom of this. And this is one reason why a kid might be good in isolation on the different problems that you're being asked, but when you combine it into these different parts here, to rip it apart and go forward and backwards on that problem-solving analytics can be confusing. I agree with that. And again, that's one reason why I'm doing these. And that's one reason why right now you're going to take that like button and you're going to smash it and you're going to subscribe to this channel. Yeah! Okay? All right, so that's what's going on with 47. Yeah, I think we said about that very well. Okay, let me make sure that's, I keep trying to fix this when I'm offline. I don't know why it's falling off the top of the screen. It's not supposed to be. I'll worry about that later. So here we have what seems to be very little amount of words, and yet most kids got this question wrong. So Leslie says that 5 multiplied by an even number always results in an even number. Is she correct? Okay, so you could know the multiplication rules. So what we need to be exploring basically is an even times an even equals what, and an odd times an even equals what. Okay, and on the same thing we can flip the two of these, which is an even times an even equals what? And then an odd times an odd. Whoops. Wait 1 second. Let me get rid of that. I didn't mean to write the O there. And then an odd times an odd equals what? Okay? So if you don't memorize these rules, it's often handy to do a little experiment again. And if you don't know it, there's no better time to do an experiment than when you're being asked to solve a question. So normally you want to use small numbers because, for instance, if we used, we're gonna check this out. So if we use like 246 times 198, right? Those are two ugly numbers that are going to give us an even bigger ugly number. So let's choose small numbers like 2, 3, and 4. Okay. I like to. Sometimes you can use 0 and 1. I like to avoid those because sometimes identities come up and you get misapplied experiments where it turns out the answer turns out to be correct just half-heartedly. It's not really the reason. Even avoiding 2 sometimes can be there. So let's use 3 and 4. So we're going to use a small, even, and odd numbers, okay? And then just work from there. So if we were to test the E times the E, we could do 4 times 4, and we get 16, okay? We can do 4 times 6, and we get 24. Okay? We can do 4 times, let's even say 10. We're trying to make this easier on ourselves. So 40, right? We can do 4 times, you know, whatever you want, 22. Just as long as you can get an answer quickly. So it's noticing in all cases that E times E is an E. Okay? E times E is an E. So if we do the same thing with the 3 times 4, we have an even times an odd. Oh, wait a second. Give me 1 second. That was supposed to be... Wait, still don't have that right. This one was supposed to be the flip of those. So I have an odd times an even. That's equal to 12. So far that's even. Okay? If I have an odd times an even, that's equal to 18. That's also even. I have an odd times, let's say 10 to make it easy. Okay? We get 30. That's also even. And let's do one more. I have, we can even use the same number we did before. 3 times 22 equals 66. So that's even. So it turns out an odd times an even is an even. And if we were to flip each one of these, we get 4 times 3. So that's 12. Flip those, we get 6 times 3. We know that's 18, so that was even. We're going to flip these, so we get 10 times 3. That's 30. We know that's even. And we're going to flip this again. 22 times 3 is 66. So this is even. Okay? So an even times an even is an even. An odd times an even is an even. And even times an odd. And now we an odd times an odd. So we can do this straight up. 3 times 3. That's equal to 9. So that's odd. Okay? We can do 3 times 5 and get 15. That's odd. We can do 3 times 11. Okay, that's 33. That's odd. We can do 3 times, what's a good odd number? We can even use 1 in this example. I said to try to avoid that, but we still get 3. Let's do one more. 3 times 33. And we get 99. Okay, so that's showing in each example we get an odd. So that's our rules. And we can build this table up if you want. But if you notice the pattern, the only one that's not even is odd times odd. Okay? Right? Okay? So that's our table. You can memorize this. And this is multiplication. There's also rules you can use for even plus odd combinations like we just did. There's going to be 4 of them again. Even plus even plus odd, and odd plus odd. Okay, that's a different question. So let's go back to the question. Leslie says 5, which is an odd. So we have 5 multiplied by an even is equal to even. Okay, is she correct? So let's use some experiments. 5 times an even is 2 is equal to 10. That's even. Okay, 5 times 4 is equal to 20. That's even. 5 times 10 is equal to 50. That's even. 5 times 22 is equal to 110. That's even. Okay, so it's showing in all the example that's being given here that's our scenario. So explain your answer. So you can give the examples and base them on it that by experimentation you're showing that that's the case. And this is your support. All of this here, and you don't have to go the full mile on all the examples I give. This is your support. You came up with a hypothesis, or Leslie did, and you're trying to prove it. Well, you're giving actual support. Now, it could turn out that there's scenarios, pathological situations, where there's other numbers that we can use here that don't quite pan out. And it turns out that these rules I've been doing here, they break. Well, the truth, I'm telling you now, that doesn't happen. But you'll want to show that support. This also, by the way, deals with your use of the multiplication table. Okay, and it's also in an odd way about multiples, except in this case, the multiple is always even. It's 5 multiplied, multiple, by some even number. So instead of 5 times 1, 5 times 2, 5 times 3, right? And we can look at it instead of doing 5, 10, 15, 20, we're doing 5, right? It's a multiple, but an even number, right? So we're counting by tens at that point, because it's every other one. It's going to be by 2s. All right, so 5 times 2 is 10. 5 times 4 is 20. 5 times 6 is 30. You notice it's going by tens once we start the table going. All right? So we have things like there. By the way, this also deals with number types. There's certain types of numbers like integers, fractions. There's also categories like this, even versus odd. Okay? And it's also dealing with number properties. Do you know the properties of numbers? So that's what it's testing you here. Okay? So that's more or less what it's looking for you to give that support and show your example and rationalize it out. Okay? So that's your explanation in this case. These are math facts. This table right here is a math fact, and you have to give this support for the fact. So as if you're detecting this for the first time, the first person to ever do this kind of a thing. All right. Okay, so the next question. Let's see how we're doing here. We're at 48 minutes. I'm wondering, let's see, I have 1, 2, 3, I have 4 problems, and I may have done 4 already. I wonder if I should even split this up into 2 parts. I'm going to try to go for it so it's all together on one case, one scenario. So enough kids got this wrong too, but not as many as the other ones. All right, so let's go for it. It's a word problem. Mrs. Ruiz bought 5 bags of balloons for a party. So 5 bags, we're going to stop. Each bag contains 70 balloons. So we're going to kind of have some of the same thing. So there's 5 bags bought. One bag has 70 balloons. So that's our ratio. Each bag has 70 balloons. Did I spell that wrong? I don't know what I did. Yeah, I spelled it wrong. Uh, Andy said she bought a total of 75 balloons. Is Andy correct? So it seems what Andy did was he took the 70 balloons in one bag, and then he added it to the number of bags and got 75. But this is balloons per bag, and this is just bags. So we're combining on like terms. You can't do that. So Andy is wrong. Andy is wrong. So just like the example a couple of questions ago, we could have done 70. It's one bag and 70 plus 70 plus 70 plus 70 plus 70. That's 5 times. And if we add that up, we get 350. This is our repeated addition. Or we could have done 70 times 5 and gotten the 350. Okay. What some students do is they don't leave that alone and they add the 70 back into there. Okay. It's not 350 plus 70. Okay. That's just going too far on this. Okay. There's 5 bags, each with 70. When you add them up or multiply them out, you get 350 balloons altogether. Okay. So the first is what error did he make? The error is combining different things. What is the total number of balloons? That's the 350. Okay, so this one wasn't too bad from that perspective. This is about, again, knowing your multiplication table. This is about knowing your rates and ratios. And by the way, if I write that ratio, I'd have 5 bags. One bag was 70 balloons. I'm just going to put BAL. And the question is 5 bags is how many, right? So we can do that cross product again. 70 times 5 equals 1 times x, which is x. And then we have down here, which was what we had here. So we know that's 350 at this point. So again, each of these is a ratio, and together they're a proportion. But the final ratio with 5 is the 350. Okay, and you can simplify that. 5 goes into this one time, 5 goes into that 70 times. Booyah, we got the answer back. All right, yay. So the 70 plus 5 is no good. The repeated addition works. And we can also have done something like set up, do 70, 140, if we keep a running sum, 210, 280. And if we do that 5 times, we finally get up to 350. Booyah, that works as well. So these are all just shorthands of basically avoiding the 70 times 5 multiplication. So, but they're all there, and they're just different ways to look at the problem. And the key to a lot of these, and I really haven't said it as strongly at this grade level, is to try alternate ways to double check your answer. One of the problems students have is they double check their answer by doing exactly the same thing. And that if you made a mistake the first time, you're probably going to make the same mistake the second time. Okay, so this is dealing with, again, the concept of a whole. The whole is how many are in all 5 bags versus the whole of 1 bag. Okay, and by the way, this is not comparing 70 versus 75. Okay, this is not what this question is about either. Okay, and it's about multiples as well. It's also about multiples, which again gets back to your multiplication table. So like we're running into the same theme every single time. All right. Let's see here. What else can I say? Yeah, and by the way, some students. Yeah, let me just leave it at that. And again, we can use this as the hint, telling us how many are there. A band has 36 members. They are arranged into 6 equal rows. 1, 2, 3, 4, 5, 6. Right, I'm going to take it a sentence at a time. The band has 36 members. Let me make sure that's on your screen. I'm not sure I checked that on the last example. Sorry if that flipped off. For anybody who doesn't catch it, where is that? In case you didn't catch it. Oh, I was scrolled past it, so it should be there. Anyway, that was the question there. I'm going to leave it there for a second. You can pause, screenshot it, whatever. A band has 36 members. They arrange in 6 equal rows. How many band members in each row? Well, we can start dotizing them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. And that means if we count now each of these, we get 1, 2, 3, 4, 5, 6. And make sure my dots are right. 1, 2, 3, 4, 5, 6. I have no remainder and I have no open spaces. So there are 6 in each row. Okay, that's a visual way to do a division, which is 36 divided by 6 equals 6. And we can prove it because 6 times 6 equals 36. So again, this is about a whole, all 36, equal parts. There's 6 band members per row, right? So we have equal parts. So it means each row is 1/6. This is the 6th. This is a 6th. This is a 6th. That's a 6th. And that's a 6th. And we know if we were to add them up, a 6th plus 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 a 6th is equal to 6 6s. And that's equal to 1, the whole. Yeah, the whole rules here. So we have equal parts. They're all the exact same fraction size. They're all 1/6. Okay? Okay, so let me scroll this slightly. So it says, can the same 36 band members be placed into exactly 7 equal rows? Why or why not? Okay, so if we were to kind of set this up the same way, we have 7 rows, 2, 3, 4, 5, 6, 7. We can go through that same thing. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. Look what happens. We have an extra one here. And if you notice, this is the 7 times multiplication table. Right? So we get 7, 14, 21, 28, 35, right? Because 7 times 5 is 35. If we look at this as 1, 2, 3, 4, 5 going on, we basically set up when you have 1 left over, right? Because 7 times 5, why did I write it 3? 7 times 5 is equal to 35. 7 times 6 is equal to 42. And if we fill that out, this is the 36th one. 37, let me just write it, 38, 39, 40, 41, 42. So you see how it would have filled up if we did that? So if we go back to the question now, and by the way, we can do this as a division problem. You know that 36 divided by 7 would be equal to 5, remainder 1. We can also write this as 5 and 1/7, okay? Depending on what your teacher's looking for, or the test, or whatever you're doing. Those are our 2 things. So we have remainder 1 here, Okay, that's the same as this one here, and that's the same as this extra dot right there. Okay? So again, we're talking about equal parts. In this case, unequal parts. Right? It can't be done because there's an extra person left over that can't fill up a row properly. All right? If it's per 6, if there's 7, it means there's a row with only one person in it. So it's not exactly, right? Exact equal rows they're asking here. Let me scroll that down in case it's not showing up. So again, it's about equal parts versus unequal parts. We're running into the same kind of different things here. All right? Multiplication table, parts of a whole, sum of a thing, yada yada, fractions, the whole shebang. And by the way, this also deals with factors, right? The factors of 36, if we were to write them out, we get 1. I'm going to write the other number over here, 36. 2 and 18. 3 and 12. 4 and 9. 5 is no good. 6 and 6. So that's our factors of 36 there. It's asking for 7 rows up here, right? And 7 is not any factor. So therefore, 36 can't be split up into 7 equal rows because there's no whole number integer factor that is 7. So we could have solved this with factors as well. All right, so this is, as you can see, how the concepts and topics and stuff all kind of stop merging around with each other and so on. We could also count up. Did I give that example before? No, I didn't, but we could have counted up. That we could have done 7, 14, 21, 28, 35, right? 42. Okay, so if you notice, we skipped there. There's no 36. So we can't, if we do this as a multiple perspective, we can't get it done from that perspective as well. And of course, you guys should know that 7 times 6 is equal to that 42 there. And we can see it's 1, 2, 3, 4, 5, 6. Okay, so again, it's getting back to your multiplication table. We're running into the same theme over and over and over and over. And by the way, when you get this extra dot here, some kids can get that far, and then what they do is something like 36 minus 1. 36 minus 6. Instead of taking 1 off and saying, oh, there's an extra person, they end up getting 30 here. They're like, oh, that's a good whole number. It sounds right. No, that's no good either. That's really off in left field. It's just nothing at all to do with this problem. It's just a total distraction, and it's a misunderstanding of what's going on in this problem, in the question and in your own solution. It's not even upside down. It's really pretty far out there. So it's something you guys need to consider. All right, so the next problem is a good one. Let me just see for a second how many problems we have left. Okay, we only have 2. So what I'm going to do is do the last one first and do that one by itself. Let me make sure this is showing on your screen. Because that other one, there's a couple of solutions to it. I want to make sure that we're getting it done cleanly. So we have an illustration. I see a pencil case is $3. A crayons are $4. A pack of folders is $2. These are supplies for a classroom. Okay, this is the supply here, and this is the respective cost for it, right? A box of crayons is 4. A box of crayons is not 3. Okay, and I've mentioned in other videos about adding stuff up. So 7, 9. In this case, they are probably not going to ask us what is the price of a pencil case and a crayon and a folder. It's probably going to be assorted different multiples of them. So this is what I was saying before. You don't know how far far to go in looking at your illustration. So at this point, let's leave it. When I did it in those early examples on the other videos, it was only for exploratory purposes, but it's showing you kind of where you should be starting to stray on some of these. Okay? And it might be they do ask us, what is the total cost of a pencil case, a crayon, and a folder? Okay, but most likely they're not going to do that. So let's go to the words, because this table is pretty grokkable, and there's nothing really too weird or bad in it. Before I do that, I'm just going to erase what I just did here, just in case I need to write other stuff on here, because this is just exploring it, trying to understand what the table is about. Okay. Okay, so Ms. Amani and Mr. Blake each ordered classroom supplies for the thing, and that's pretty much what we grokked out of this so far. The cost of supplies is shown below. Okay, that's this here. All right, cool. So there's really nothing extra they're going to be telling us there about things. Miss Amani ordered, so we're going to say Amani ordered 7 pencil cases and, which is addition, 9 packs of folders. Okay, so that's my notations. Mr. Blake ordered 9 boxes of crayons. Do you see how I did that symbolically? And then it says, what is the difference in the cost of supplies that they both ordered? So it seems to me I need to figure out the cost of what Amani did. So Amani did 7, right? She ordered 7 pencil cases at $3 each. Right, so that's my P. My P is 3 there. And 9 folders. Right, so we're going to multiply that by the price per folder. So that's 2. Right, so we end up getting 21 plus 18. And when we add that up, we can do it like that. We get 9.3, right? So that's equal to 39. Okay, Blake, he had 9 times the cost of a crayon. So that was 4. So that's equal to 36. So Amani paid $39 for her supplies, and Blake paid $36 for his supplies. So at this point, enough kids will say the answer is 36, but that's not what the question was. Okay? They just think it's the last computation they did, and therefore that's the answer. But it's a word question involving a visual, a chart. So if, never just get your last answer and go on to the next question. First of all, you want to double check and see that what you did was correct. But what happens is, because of that, your brain gets distracted and it thinks, oh, I did all these computations already. I'm done. I'm tired. That kind of a thing. You don't really want to go there with this. All right. So let's reread everything and look at everything again. Miss Amani and Blake ordered supplies. Cool. The cost is shown below. Cool. Here's the cost, the table. Amani ordered 7 pencils and whatever. Cool. Blake ordered 9 boxes. What is the difference in the cost of supplies? So this word here, difference, is a technical term. It means subtraction. It means to compare the 2 values. It means to compare 39. Let me write that better. 39 and 36. And that would be equal to $3. The difference between what they both paid was $3. Right? If I give you $5 and I'm left with 3, the difference between 5 and 3 is $2. So that's what they're asking us here. So what is the difference between what the one ordered versus what the other ordered? Okay? So the answer is 3. Some kids, because this says and right here, they do 39 plus 36 and get 5, they get 75. That is not the answer. That is not what you're being asked to do, right? A lot of you are told to look for keywords like total and stuff like that, and the word and means addition, but it doesn't work in all cases, and you have to apply the logic to it to make sense. In this case, it actually meant addition, but you added the wrong 2 things. Okay, but in this case it meant difference, so it actually meant subtraction. So it can't mean the subtraction of the addition of two things. That what? It meant I have two things that's trying to compare. Amani versus Blake. What's the difference between the two of them? That's what it was asking you guys what to do. All right. So again, this problem dealt with a visual. It's a word problem on top of that. It's dealing with multiples, right? In this case, it's a multiple. All right, let me change the color of this for a second. Let's use dark green since we haven't done that. Here's a multiple: 7P, 9F, 9C. And to actually do those multiples, we actually have to do the multiplications. So we need to know the multiplication table again. We could have done for this one 7 plus 7 plus 7 plus 9 plus 9. Okay, but again, just knowing the multiplication table, bing, bang, boom, you're right there, baby. Right? That kind of a thing. So that's where you want to go with that. This also dealt with operations. So now we're seeing something like this 9P. Change the color one more time again. This 9P plus the 7P plus the 9F, that's getting to be more involved arithmetic. All right, so we're combining stuff. So what we have is equal parts. This was the equal part, that each pencil case was 3. Each crayon was 4. Each folder was 2. Okay, and at the end of the day, even though we're adding unlike things, pencil cases and crayons, we're adding their value. We're putting meaning to the combination. So here we're getting the whole part would be the 39 in the case of the pencils and the folders, and 36 is the whole part of that, right? So this was, in the case of the crayons, it was split into 4 parts. Because it was split into 9 parts, because there's 9 of them. Okay, here we're doing sum of part. We have 1/7. Each folder here is 1/7 of that total, but it's the super additions that we're looking at here too as well. All right, and this slightly deals with the order of operation PEMDAS. Please excuse my dear Aunt Sally, which is that if I had the 7 times 3 plus the 9 times 2, you have to know to do this first and get 21, and this first and get the 18. This is not 7 times 3 is 21, and we add 9 to that and we get 30, and then we take the 30 times 2 and get 60. That is not what PEMDAS tells us to do. So you need to know your order of operations. They're normally explored later on in the year, and they really hit home in later grades, but these are still notions you should know how to do. And we're really looking at this as if it was parenthesized. 7 times 3 plus 9 times 2. Okay, and we do the parenthesis individually. Okay, and so one way to think about this is if the parens are not there, we have to implicitly add them. Okay, that's another way to approach some of this. All right, so we're going to go back to that other problem, which is what's a composite shape, because it's made up of a bunch of shapes. Okay, and let me make sure that's on the screen. This is a slightly different question that we've been doing for all of them. In fact, this is what I'm going to do. I'm going to end this video right now and do this one by itself because I'm looking at this now. Almost every child got this question wrong. I think only 30% of something got it right. So that's a huge number of kids got it wrong. And then we can kind of beat it up with this own video. So please like, please subscribe. You guys need questions, you have tutoring, whatever, hit me up. Okay, and I'll do the other one. I'll post it along with this because I'm on a roll and I want to get past this. So I'm going to start up the other one and post this, probably the two of them together. All right. Peace, y'all.